gradient small. Okay.
Thanks. Okay, this is joint work with Dylan, Ayush, Ohad, Nadi, and Kartik. So in recent years, there's been a great amount of effort devoted to trying to understand non-convex optimization. Nevertheless, there are still a number of questions that remain open, and this is kind of in stark contrast to the situation in convex optimization, where for kind of a huge variety of problems, we really tightly understand both the complexity of optimization, and we also have optimal algorithms for doing so. So kind of what we'd like to do is somehow use this knowledge from the convex case as a guide towards understanding better non-convex optimization. But one difficulty for doing this is that the goal is changed. So in convex optimization, we try to find an approximate minimizer of the function. But in non-convex optimization, we have to fall back to finding an approximate stationary point. And there's a good reason for this. In general, we can't hope to find an approximate minimizer of a non-convex objective. Nevertheless, this is kind of a challenge to move forward. And for this reason, we focus kind of on an easier problem, which is seeing what we can do in the convex case to find approximate stationary points. So we consider a stochastic convex optimization problem where the objective is the expectation over some unknown distribution, and where the population objective is H-smooth, meaning that the gradients are H-Lipschitz. We consider optimization under sort of three types of access to the function. So we have first order access to the objective itself. We have stochastic first order access to the objective via these component functions. And we consider a third case in which you get samples from the unknown distribution and you have full access to the component functions. And this sort of gets at the sample complexity of the problem. And the goal here is to understand how many queries of these types are needed in order to find an epsilon stationary point of the objective. Okay, so in the case of a deterministic first order oracle, Nesterov and Carmona et al. Have already kind of answered the question. So they provide tight upper and lower bounds on the complexity. And I want to point out a key feature of these, which is that it depends on sort of the square root of the smoothness parameter. And there's kind of a good reason for this. So if you look at the example here on the right, this is a non-smooth problem where it's very easy to find an approximate minimizer, but to return a epsilon stationary point, you have to exactly hit W star to infinite precision. And it seems fairly clear that using just first order information, you're kind of never going to be able to land right on the bottom. Okay, so that's sort of the answer for the deterministic case. What happens when we have stochastic function access? So you'll notice that in the deterministic case, the optimal algorithm here is accelerated gradient descent, which is optimal both for finding an approximate stationary point and also for finding an approximate minimizer. So for this reason, you might hope maybe sort of the same stochastic first order algorithms that we use to find a small function value might also be useful here in finding an approximate stationary point. So one thing you might look at is what SGD can give you. So it gives you some guarantee. It doesn't look very good. You might hope to improve upon this, and indeed you can. So Alan Zhu last year presented a more sophisticated algorithm called SGD3, which substantially improves upon SGD. So now in sort of the, if the story here is anything like in sort of regular convex optimization where you're trying to find a small function value, you might hope to be able to improve this first term to match the deterministic first order complexity. And indeed, our first contribution is to provide an algorithm that does just that, reducing the first term, and we also prove that this is the optimal rate. So again, just as in the deterministic case, we have this square root of smoothness dependence, and again, there's kind of no reason to expect better than this. You really can't expect to find the bottom of this example here without sort of an unbounded number of queries. So with first order information, we can't really hope to improve upon square root of h. But what about if we have more thorough information, like global information? So in particular, if we have access to these samples from the distribution and full access to the instantaneous losses, can we improve upon this? And the answer is yes, we can. So in fact, we show that the sample complexity is nearly independent of the smoothness, depending only logarithmically on h. And in fact, the best lower bound actually does not preclude the possibility that there's no dependence at all on H. So this is kind of really good news in the sense that even for very non-smooth problems, we can hope to find an approximate stationary point using a very small number of samples. And I also want to point out that even though the algorithm that achieves our upper bound requires solving a series of regularized empirical risk minimization problems, you don't have to solve them exactly, and they can actually be implemented using fast first-order finite sum algorithms such as SVRG. Okay, so as I've shown, there's sort of this exponential gap between the dependence on the smoothness in the first-order case and in the sample complexity case. And you might, as the lower bound did not, looking at the lower bound, it's not clear even that you need to depend on the smoothness at all. And in fact, we show that in one dimension, when the objective is univariate, actually ERM with a small number of samples will actually output a point with a small subgradient, even if the function is non-smooth or not even differentiable. So this example I've been scaring you with the whole time, actually ERM would return exactly W star. Okay, so let me give you a quick idea of how our algorithms work. They're based on, sort of inspired by this SGD3 algorithm from Alan Zhu, and it takes sort of a recursive regularization approach. So the sort of foundation is this meta-algorithm where we construct a sequence of subproblems by augmenting the objective with a series of increasingly strong regularizers that are centered around approximate solutions to the previous subproblems. And what we do in each round is we approximately solve these subproblems using an arbitrary plug-in solver of your choice. So we've shown the analysis that after a small number of rounds, the norm of the gradient is bounded by a weighted sum of the optimization errors given by these subroutines. And so by analyzing how close your plug-in solver gets to the solution, you can upper bound the norm of the gradient. So in particular, we show that by pairing this meta-algorithm with ERM as the solver, we get the nearly optimal sample complexity up to this log in H term. And we show that this meta-algorithm plus an accelerated stochastic gradient descent variant gives the optimal stochastic first-order complexity. Yeah, so that's all for now. Please come to poster number 178 to talk more with me and my co-authors.